मी लिहून घेतो डायरेक्ट.
वाळके सरांना फोन करून दे.
हो
जा ना, काही प्रॉब्लेम नाही. काय घेऊन जा ना. गुड बॉय. कुलकर्णी मॅडम फोन करते, करा बरं त्यांना. माझा फोन तिकडे बिझी आहे. नाही त्या काय लिहिले याच्यात फक्त एकच व्यक्ती येईल, खटाळे सर, बाकी कोण नाही. त्यांना केमिस्ट्री मध्ये इंटरेस्ट तयार झालाय. पवार सर त्यांचं BSc MSc करून द्या ना केमिस्ट्री मध्ये.
पाळेकर सर, तुम्ही मेल केला का मला? हा बोल.
पवार सर मॅडम होते का आता?
पाळेकर साहेब.
नाही तुमच्या बाजूला.
कसं दिसतं काय पाहिलं?
इकडे दिसलं ना म्हणून म्हटलं. पाटील सर आले बरं.
सर करू का फॉरवर्ड?
पाटील सर.
सर
बघा जमलं का बघा. स्क्रीन जमली का बघा.
स्क्रीन बरोबर आहे. राईट. अरे वा, व्हेरी गुड. थांबा, स्क्रीनशॉट घेऊन ठेवतो. मस्त. आयला कलाकार आहे तुम्ही.
मोरकर सर होते.
मुदगल सर
होते ओपन.
हो सर.
कलाकार आहे का जादूगार आहे?
धावत पळत केलं सर. आता जेवढं जमलं तेवढं अजून करायचं होतं, पण जाऊ द्या. घेतला स्क्रीनशॉट? नाही आहे.
लिंक सेंड केली बरं का सर मी.
सर मी जाऊ का तिकडे? म्हणजे झाला स्क्रीनशॉट घेतला का तुम्ही? पवार सर.
हा बोला.
तुम्ही फ्री असेल तर कुलकर्णी मॅडमला फोन करता का? माझा फोन तिकडे आहे सर. त्यांचा माझ्याच्यावर कॉल येऊन आला होता, पण माझा फोन तिकडे आहे.
करतो.
जाधव सर आलेले आहे.
हा मॅडम, जॉईन नाही झाला अजून तुम्ही? लिंक तुम्हाला सेंड करू का? नाही काल जी लिंक सेंड केलेली ना तीच लिंक आहे. नाही आपल्या ग्रुप मेसेज वरती डिअर पार्टिसिपेंट वगैरे आपण तीच लिंक ओपन करायची. तुम्हाला नाही आलेली. आता जी आली, आता जी भेटली ना त्याच्यात जॉईन होऊन जा.
एका मोरणकर सरांनी बाळू पवार सरांचा फोटो लावून दिला स्वतःच्या जेव्हा. हा काही नाही, तुमच्या याच्यावर बाळू पवार सरांचा फोटो दिसत होता. कुलकर्णी आल्या.
मुदगल सर,
येस.
तुम्हाला ते एक पीपीटी मिळाली का? इंट्रोडक्शनची पाळेकर सरांनी पाठवली ती काल.
नाही, मला फक्त हे एवढं मिळालं होतं. हे बघा, हे
ग्रुप वरती टाकलं होतं बघा.
हे बघा, हे मिळालं बस.
नाही दुसरं बी पाठवतो. काल ग्रुप वरती सेंड केलेलं आहे सरांनी. म्हणजे
एवढं आहे माझ्याकडे.
इंट्रोडक्शन चालू असताना ती फक्त एक स्लाइड लावून द्यायची.
अच्छा, ती का?
हो.
एक मिनिट थांबा. हो, ती टाकली आहे सर.
घ्या पुढे.
हे बघ.
सर त्यांनी रिक्वेस्ट पाठवली आहे, प्लीज ऍक्सेप्ट करा ना.
काय नावाने आहे?
प्रवीण वाळकेच असेल ना.
प्रवीण वाळके. नाही, वाळके म्हणून नाही आलं सर कोणी अजून.
प्रवीण बघा ना, प्रवीण.
फक्त प्रवीण आहे, फक्त प्रवीण म्हणून आहे.
करा 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 करा.
बघा, तेच आहे ना.
हॅलो, अनम्यूट करून टाका. पवार सर मेल केला?
हो, मेल केला.
बरोबर.
वाळके सर, तिथे अनम्यूटचा पॉपअप येत असेल, त्याला हे करा, क्लिक करा.
येतोय आवाज?
हा, येस.
मुदगल सर, ऍक्सेप्ट करूया आता बाकीचे पार्टिसिपंट्स.
एक मिनिट, पहिले मला
करा मग. आपले मेन लोक आलेत, पॅनलचे लोक आले.
कोण बोलणार आहे? बाळू पवार सर बोलणार आहे, ऑडिओ व्हिडिओ ओके आहे.
मी
वाळके सर बोलणार आहे, ऑडिओ व्हिडिओ ओके आहे. तुम्ही बोलणार आहे, तुमचा व्हिडिओ बंद आहे. चालू करून टाका. व्हाईस प्रिन्सिपल सर आहे, त्यांचा ऑडिओ आणि व्हिडिओ बंद आहे सध्या. तर मी सरांना म्हणतोय ऑडिओ चालू करा म्हणून. पाटील सर, तुमचा ऑडिओ चालू करून द्या. घेऊ का
सर?
हो सर, येस.
चालू झालंय ना?
हो, झाला सर, चालू झाला.
मी थोडं अंतर
पाटील सर,
चला घेऊ का मग आता पार्टिसिपेंट आतमध्ये?
हो सर, घ्या.
एकदा पार्टिसिपेंट्स आले की कोणी बोलू नका मध्ये. मी इथून सगळं सांभाळतो.
ओके.
पार्टिसिपेंट्स आल्यावर काहीच डिस्कस करू नका. जे करायचंय व्हॉट्सअपवर डिस्कस करा. मी स्टार्ट करतोय. 1 2 3. त्यांचा बॅकग्राऊंड नॉईज येतोय, तो त्यांनी हे करून टाका, थोडं कमी करा. बॅकग्राऊंड नॉईज येतोय.
मुदगल सर, प्राचार्य सर ट्राय करतायत बघा ना.
नाही सर, नाही आहे.
नाही ना ते
नाही आहे तर नाही सर, याच्यात लिस्ट मध्ये नाही आहे सर.
सर येतील ते बहुतेक. मी त्यांना मेसेज पाठवतो परत.
I request all the participants to please switch off your videos. Switch off your videos. Harshal, Umesh Chauhan, please do not switch on your videos. पवार सर
येस
ऑडिबल आहे ना?
बोला.
पाळेकर सरांचा
हो.
व्हॉइस येत नाहीये का?
आहे सर ऑडिबल.
हा पाळेकर सर,
हां
हा कॅन वी स्टार्ट नाउ?
ओके.
ओके प्लीज सर.
Hello. I will start with the formal webinar. Very good morning to all. It gives me immense pleasure to welcome all the student and faculty participants for this national webinar on nanomaterial past, present and future organized by Gokhale Education Societies, Arts, Commerce and Science College, Jawahar, Palghar, Maharashtra. On the behalf of Department of Chemistry, I, Dr. Vikrant Palekar, heartily welcome President of webinar, respected Principal Mishram sir, Vice Principal Dr. Anil Patil sir. I also take this opportunity to welcome our resource person, Honorable Dr. Praveen Walke sir. As per our tradition, we start every auspicious occasion by lighting of lamp. As we know that light is the universal symbol of truth, knowledge, and understanding. Let us inaugurate this webinar by lighting the virtual lamp and pray divine power, Lord, that let us take away from this pandemic condition and expect normal life ahead. Now I take this opportunity to thank our resource person, Dr. Praveen Walke sir, for accepting our invitation and present among us to motivate participant friends. I request Dr. Anil Patil sir, on the behalf of our college, please hand over virtual flowers to Dr. Praveen Walke sir. Thank you very much, sir. Let me give a brief introduction about our college. It is located in Palghar district of Maharashtra and which is considered to be a tribal, rural and remote part of one of the historical taluka among the Maharashtra. It is a hilly area and it is located in the Western Ghat. As we are going through the pandemic situation, as a result of that, we are stuck in our homes from 21st March. School colleges closed almost from 17th March in Maharashtra. But as Indians, we consider every challenge into opportunity. Our staff is also work hard in this condition. I must predominantly mention here in this particular conditions also, we have conducted 9 webinars till now, and this is the 10th webinar presently we are hosting. Our Department of Chemistry is having 7 staff members, and our goal is very student centric. So webinar we are organizing on the behalf of Department of Chemistry, especially for the students. Apart from that, we have also conducted 4 collegiate chemistry aptitude test and awareness program. I mentioned that we are conducting this particular webinar for students to throw light on their new branches of chemistry. As a part of that, we are conducting this particular webinar. For this webinar, we have received overwhelming response. Around 333 participants were registered, and these participants are from all over India. Our participants which are representing almost every state of the country. I must proudly mention that we are also participants across out of the India also. So we can say this particular webinar, president of this particular webinar, Dr. Vice Principal Dr. Anil Patil sir, to please give his inaugural address on this occasion. Anil Patil sir, please.
Yes. Am I audible? Hello.
Yes, sir.
Am I audible?
Yes, sir. Yes, sir. Yes, sir.
Hello.
Yes, you're
Yes,
audible.
sir.
Okay. Thank you. Good morning, everyone. Honorable speaker of the today's webinar, Dr. Praveen Walke, and all participants. It gives me an sorry
Hello.
for disturbance.
Sir, you can continue.
Sorry for disturbance. Yeah. Good morning, everyone. Honorable speaker of the today's webinar, Dr. Praveen Walke, participants, it gives me to extend very warm welcome on nanomaterial past, present, and future scenario for the student and faculty organized by the department. Whole globe as well as India are facing pandemic situation occurring due to outbreak of the COVID-19, and we all are locked in our home from more than 2 months. Everyone is worried about the education, job availabilities, income as well as future opportunities after the end of the lockdown and end of pandemic disease COVID-19. According to experts, intend that the need of the today's nanomaterial are future of the tomorrow's requirement in all aspects. Even you will know about the use of nanomaterial to prevent in spread of coronavirus as well as its use for drug delivering system. Many experts also say that the pandemic COVID-19 should be considered as an opportunity intent of the problem because the demand of the many products are increased. This situation like medicine and other pharmaceutical and chemical industries. I am proud of our college department are taking such questions for discussion in this webinar. I hope the ideas discussed in the webinar to percolate and reach needy one so that they to benefit. I am proud of our college are taking such questions for discussion in this webinar. I hope the ideas discussed percolate and I welcome to Dr. Praveen Walke sir, Assistant Professor, National Center for the Nano Scenario and Nanotechnology, University of Mumbai. I welcome you all against to this national webinar and hope that you all will be a great time ahead. Thank you. Thank you, sir.
Thank you very much, sir, for your inaugural address.
Thank you, sir.
Thank you very much. Now we will move forward. I request my colleague Dr. B.V. Pawar sir, please give introduction of today's resource person, Dr. Praveen Walke sir.
Thank you, sir. Good morning to everyone. For me, it's a great honor and privilege to introduce today's keynote speaker of this webinar, Dr. Praveen Walke sir. Sir, when I read your CV for a minute, I was puzzled that what should I tell about you in introductions. Sir, CV was very strong. Sir, achieved a lot of things in very small period of time. I pointed out some points here that sir presently working as an assistant professor in National Center for Nanoscience and Nanotechnology, University of Mumbai. Sir did his PhD from Naples University, Federico, Italy. Sir complete his graduation in BSc as well as MSc in physics from University of Pune. Sir also worked as a RA in CSR NCL as well as South Dakota State University, USA. Sir got a prestigious award that is Marie Curie Fellow with Dr. Ulrich Luders from France. Sir also worked as a research associate, obtained Best Research Associate Award in Inter-University at Department of Physics, University of Pune. Sir also got a Raman Fellowship to pursue his postdoctoral training in University of California, USA. Sir established a research group working on energy nanomaterial as well as thin film and nano micro devices at National Center for Nanosciences and Nanotechnology in University of Mumbai. sir published more than 40 research articles in a reputed journals, and also some couple of books in his credit. Sir is a member of various national as well as international societies. Sir also reviews some reputed journal, reviewer of reputed journal. Sir is a member of Board of Studies of Nanoscience in a Dr. Babasaheb Ambedkar Marathwada University, Aurangabad, as well as University of Mumbai. With this short, that is nano introductions, again I would like to welcome you, sir, and request you to please guide us. Thank you, sir.
You can share your screen.
Yeah, sure. Can you see the screen?
Yes.
Not yet. Yes, it is now open.
Okay, very good morning, all of you. And I would like to thank organizers for being here. And it is very nice introduction by Professor Pawar. And I was not expecting this big introduction of mine. Anyway, thanks a lot for having me here today. So as I understood that this webinar is specially organized for the students, especially the bachelor's and master students. So I made it very informative, and I tried to make it more general so that everyone will understand what will be explained in this webinar. So the title of this presentation today is Nanomaterials, Past, Present, and Future Scenario. So let me show you the outline of today's my presentation. Here, initially, I will introduce a little bit about the material science, then why physics, chemistry, and engineering of the materials has to do, what to do with the material science, then what material scientists can do in this case. Then there will be some selected examples I would like to showcase so that you will get a feel of nano. Then important challenges in this field, then what are the career perspectives, and finally I will conclude the talk. But before going into the detail about the talk, I would like to make it more generous so that you will have a tour of nanotechnology, little bit of flavor of what nanomaterials are doing. And in this case, past, future, and present. So all those things will be one after other. So I am not having the presentation like, let's look at the past. It is synchronizing all these past, present, and future. Okay, so let's have a look on this slide. So you can see here materials. Where are the materials present? If we see around us, there are everything made up of the materials. Therefore, materials are playing major role in everybody's day-to-day life. So why to study this material science? Because to understand the materials, you need to have the knowledge about the physics, you need to have knowledge about the chemistry, and also the engineering of all those materials, and it will play an interdisciplinary theme about everyone's life, especially those who work in the science field. But I tried to make this presentation which can understand by the layman perspective as well. So it will be very easy for all the science students to easily grasp all these things. So I hope that you people are understanding. First time we are interacting due to this pandemic situation in virtual world, and it's very difficult to guess what students are guessing from all these presentations. So I hope that all of you, if I ask some questions in between, you just type the answers in this message box, right? Comment box, you just drop and comment so that I will come to know that you people are attentive more enough. Okay, so let's have a look on these materials. We have the materials everywhere, every material, every matter is made up of this material. And let's have a look of this slide. Why to develop the new materials? Already there are so many materials exist around you. So why people are searching for the new materials? Is it about making a form of materials that have never existed before? So is it so? Is there any material which is not available before and we are exploring it. It's not like that. Already materials are there in the environment, there in the nature. We are just looking in the different perspective and understanding what are the features of those materials, right? So it is just a curiosity. We are very much curious about what are the materials around us and how these materials behaves. And because of the curiosity, people are going to find the new materials. Another perspective is the utility of those materials. So we need specific materials for specific applications. So if your applicability is different, you need some different materials. Sometimes you need water absorbing material. Sometimes you need water repellent materials, right? So in rainy season, we want a raincoat so that our garments don't get wet, right? So therefore we need, in that case, we need a hydrophobic materials, right? But if we are looking for, if there is a cold weather or if there is a hot weather, we need a little bit of fabrics which can absorb a little bit of moisture so that you make cool enough your body, right? So these are the different curiosities and utilities, and therefore we have to explore the new materials around us. Okay, so let's see here. There are many scientists across the world, right? This periodic table last year, 2019, was celebrated as an international year of periodic table as declared by the UNESCO. And we have completed 100 years of the periodic table. So since the discovery of the periodic table, huge development has happened and we have explored n number of elements around, right? You see here the gentleman, Glenn Seaborg, who has pointing out seaborgium in the periodic table. So that particular element has named after him and he has discovered the seaborgium. And there are so many audience who are just now listening me, probably they will have their own names or their own name elements in future if they will get inspired by this talk. I hope so. So, I wish that someone of you will pay attention about this, exploring the new material world and finding out the new elements which are already present in the environment, or you can manufacture those kind of elements in future. So I wish you all the best. Okay, let's see. This is the article which is obviously in local newspaper Marathi language, and which is exploring how this invention or journey of periodic table has been happened, and it has written on the last year on the occasion of 100 year of the periodic table. So those who understand the Marathis, they can go and read it later, and it is available online as well. Okay, so as human evolution is happening, there is huge changes in the society and human perspective has happened. Similarly, the technology through ages has drastically changed, right? So it has drastically changed. You see here, initially it was a stone age when human was staying in forest and all those things. The human evaluation, Darwin theory of evolution, you people might have studied. So this strong age, stone age, then bronze age, then after that we found the iron, then iron age. In the 19th century, it was the chemical age. A lot of chemical reformations happens, right? So metallurgy, natural materials, small molecules, all things have been explored in that season. Later on, we find out the nuclear age and plastic age. So polymers and plastic, everything come into our day-to-day life, right? So that plastic age was there, let's say around 1914 to 1916 in the 20th century, and then biotechnology come into play, biotechnology and materials age. So these are again drastic change in technology by using the biotechnology and materials. But this 21st century is going to be the nanotechnology age. Information and knowledge, nanotechnology age, this 21st century. And we see here in the 21st century what nanotechnology has done. Nanotechnology has miniaturized everything around us. You see our laptops, initially the supercomputer, which was, occupied whole room, almost a room, and then almost a room, whole computer it requires. But now you see the small laptops which can easily put into your bag, and that has miniaturized at that level. How it has happened, who has dreamed all those things, that I will going to show you in a minute. Okay, so this is the nanotechnology age of the 21st century, and we are going to see what nanotechnology is doing in our life. Okay, so let's see what material scientists can do. What is the role of material scientists are doing here? So material scientists are finding the materials for the different angle. So those novel materials which are applicable for some other things, let's say nanostructured materials. So those at the nanoscale, I will show you what is the nanoscale is. Electronic materials which are applicable based on applicability, electronic materials, biomaterials, smart materials. What do you mean by the smart material? That also I'm going to show you here in this presentation. Then soft materials, composite materials, materials for energy storage. So all those things, material scientists can find out n number of materials around. But why we need to develop those materials? What are the global challenges in front of us so that these materials can fulfill our need or fulfill the global challenge? You see the global population since 1950, the growth rate of global population is drastically changing. It is sort of explosion of population, right? And therefore, you see here in 1915 to 2050, you find out how many billions of growth rate is there, right? So there is drastic increase of population since decades, and now it will be huge in few further decades as well. So let's have a look on this another side of what it creates, what those population problems has been created. So water scarcity in the future. So huge consumption of all those natural resources, and they are the other. We will have the scarcity of these waters. We have a huge burden on our environment, right? So this water scarcity in the future is the major problem the world is going to face. Another one is the nature of global energy problems. So what are the global energy problems? What are the facts here? In this slide, I'm going to show you the global challenges, what are the facts, and what are the actions needed to do. And how the material scientists will play the role, that we will see later on. So what are the facts here is population growth is a major problem, but what action is needed? Limit of the growth of population. And we have also the limit to stop this population growth, right? So that is none of our part at the moment, but it is required to reduce the growth of population. So what are the another facts is increasing energy demand. As the population increases, the requirement of energy is huge. Industrialization, scenario is changing, so huge competition is there, so a lot of energy is required. Energy demand is huge, and therefore increasing the energy demand. So to fulfill those energy demand, we need to increase the efficiency of what energy devices we do have. So we need to increase the efficiency of that energy generation devices, energy utilization. We reduce the consumption. So low power devices is required in future. But another problem is that we have the limited reserve energy in the nature, right? Limited energy we do have. So we have to explore all the energy options. What are the energy things we can explore nearby? Let's say sun energy, wind energy, and so many things nowadays. Scientists and people around the world, they are finding out, exploring the different energy options or energy resources. And because of all this development scenario, there is huge environmental degradation has happened, right? And because of that, global warming is the major issue in front of the world. It causes a lot of adverse effects on civilization, on the nature, on the earth. So to avoid those environmental degradation, what we need to find out is new clean technology. That technology will one side fulfill the demand of growing population, smart cities, and other side it won't hurt the environment at the same time. So we have to balance all those things by using the new clean technologies. So another thing is energy, because what I'm talking about more about energy is we are especially working on energy nanomaterials. So I just want to give the flavor about what energy and electronic devices are playing role. We will come up to some of the biological applications as well. But you see the energy gap, the half of the world population which subsists an agrarian or a lower level of energy access, right? So half of the world. So the population density generally exceeds the carrying capacity of the environment. So therefore, the huge gap we have found in energy access in the urban and rural areas. Let's have a look what to do with the material science and the nanotechnology. You see here in this picture, 2 megawatt solar electricity production, okay, at SMUD's nuclear site, which is required the electricity that is generated by these 2 megawatt solar cells. So the solar cell research is huge happening, and it has more significant impact on the society as well as economy, because this is completely clean energy technology, and the technology solution can be happened through the new materials. You see here, the solar panels previously was having a large area. It requires acres of land. You see here, acres of land is required to put these solar panels, and therefore there is another problem of land, right? So how we can solve those problems? One, we have to increase the efficiency of those solar panels, and second, we have to reduce the size of solar panels. So these can be happen only with the new materials. So if we can make such new materials which can have high efficiency, and same time which is having lightweight, and same time it will occupy very small space, right? So this is there. So this is very gentleman, E.G. Kobayashi. What he says is those who control the materials, they can control the technology, right? So we are here in the 21st century to control the material, so we control the technology. So now this technology doesn't go in the hand of billionaires now. It comes into the hands of material scientists. Because if you have a very good material to solve your purpose, you will become a billionaire, right? So keep in mind, the next generation technology and economy will be based on the smart materials. Okay, here, look at the Indian scenario. In daytime, we will use the solar cell. So daytime sun is there, we can harvest the energy and produce the electricity. But what happened at the night time? You see, in Indian cities, we need huge lighting. Or all across the world, there are n number of smart cities, and all smart cities need n number of lighting and huge energy requirement. But the other side in India, you see at the villages or remote places, there is lack of electricity, right? So we have to enlighten them as well. So therefore, there is a mission where people are putting these solar panels, but though the solar panels are there, they can be useful only in the daytime. So what we need to do is we have to store that generated electricity into some storage devices, and then that can be utilized at the night time, right? So then energy storage is another sector which is very important, whole world is looking at. But what are the another issues in front of the society? You see here, this picture here, this picture clearly shows Indian roads, right? Huge traffic, especially city like Mumbai. And because of that, this traffic and transport, we are emitting a lot of carbon dioxide, carbon monoxide into the air, and huge pollution has happened because of such kind of oil-based vehicle or fossil fuel-based vehicles, right? We are burning thousands of liters of petrol and diesel, and we are producing CO2, CO, and so many hazardous gases into the air, and it is pollution. So pollution is the big problem, right? So to solve those problems, what we need to do is we have to switch all those fossil fuel-based vehicles into the e-vehicles, or 100% electric buses or zero emission buses. You see here in the picture, the electric bikes or electric auto rickshaw. So they have their own problems that going or switching to the electric field, right? So it has its own problem. What are the problems and how we can solve through the new materials, or especially the nanomaterials, how they play a role into these technologies that we are going to see. So why these challenges will be taken up by the nanomaterials that we're going to see. But these are the major concerns. So if these things, if we convert into the E, it has its own limitations, like the charging issue. If you have e-vehicles, the batteries are there, so the batteries need to be charged frequently, and it has run only few kilometers to the mileage, right? So again, you have to be charged. So the charging station is the major issue. Long-lasting battery life, battery efficiency. So many things are there. So people have thought about the hydrogen as the fuel. Can we switch this electric vehicle into the hydrogen as a fuel? I will show you one of the very nice video where you can clearly see how these battery vehicles and fuel cell vehicles works on. So this hydrogen as a fuel. So scientists across the globe, they have thought about the hydrogen as a fuel. So, but the problem with this hydrogen as a fuel is we need to have the inexpensive generation and the storage issues of the hydrogen. You see in this figure, you can see these are the different hydrogen sources where carbohydrates are there. If you burn it, you will release the hydrogen. Like we have the wood, coal, and with respect to, along with the hydrogen, there are so many other gases are emitted through this, but generation of the pure hydrogen is the major concern, that also in inexpensive way, and storage is another issue because hydrogen is explosive, right? So you have to store it really very safely. So how this inexpensive generation and storage issue will be taken up by the material scientists, right? So that is another question in front of the material scientist as a global scenario. Let's see here. This is the membrane electrode assembly. So this is the fuel cell membrane. What happened is there are the two electrodes you see. You pass at one electrode the hydrogen gas, and another electrode you pass the oxygen. And what you will find out is there is a generation of electricity by passing just hydrogen through these electrodes, right? And what would be the output is simply H2O. So you imagine if your vehicle is filled by the hydrogen gas, right? And through that hydrogen, you generate the electricity, you run your vehicle, right? But the byproduct will not be the gas or fumes of CO or CO2, right? It will be simply the water or moisture in the air. So can you believe the vehicle which is running through the hydrogen gas? But how that hydrogen can be produced, that is another issue. But recently there is a huge work happening on this kind of hydrogen evaluation. So a lot of chemists will working on the catalyst, those catalysts that photocatalyst or electrocatalyst, which can photocatalyst or electrocatalyst, which can split the waters into hydrogen and oxygen, and those evolved hydrogen can be stored into the nanomaterials or into other materials which are the porous materials, where the hydrogen will go on the carbon and form the CH bonds, and there is an adsorption of hydrogen will happen on the surface, right? So in that case, probably CNTs, carbon materials, porous carbon materials are playing a huge role to store those kind of the hydrogen. So can anyone use this hydrogen stored on the carbon, porous carbon, okay? Little bit heat, if you give to those, it will be releasing hydrogen, and that hydrogen can be used for the fuel cell. And by using the fuel cell, that hydrogen generates the electricity and it will run your car. And the final byproduct will be the H2O or the water droplets. So it is very fantastic and very clean, and it will fulfill our desire. And here you see the application of this fuel cell. This is the fuel cell car. You can clearly see this fuel cell car here, right? So you have to just fill up the hydrogen gas inside, and that fuel cell car will run. This is the phosphoric acid fuel cell. In another figure, you see UTC power. This is the first modern fuel cell type which was commercially used and found applicable in the stationary and automotive power sources. Right? So these are the application of fuel cells. So what is the trend of the fuel cell is happening since last few decades, 2 decades, and what will be the future? Here, future, I have not shown anything after 2020. The reason behind it is after 2020, the miracle will happen with nanomaterials. So what are the 3 basic areas here to get fuel cell applicability? One is energy conversion. So you have to convert this energy, let's say from hydrogen, you have to pass, and then you have to convert this energy. Second is how to store the hydrogen. As I said, you may have the porous carbon nature here, carbon nanotube, mesoporous organic networks, they can be used. Commercial technology for the mass production is on the way, and I don't know, in 2020 probably there will be the drastic change in the storage technologies as well. So the hydrogen generation is another thing. You can generate the hydrogen, as I said, one of the things that, biohydrogen, electrocatalytic, biocatalytic, and photocatalytic materials which can generate the hydrogen. Okay, so in 2020, especially if nanotechnology is leading to all these technologies, these will be the drastically changing. And nowadays, fuel cells are on the road, but the efficiency is the major concern. And nanotechnology can take up that challenge to fulfill those kind of efficiencies, right? Okay, now there is another area after energy is more important area which people are more curious about. That is the electronic devices. You see, now the electronic devices are becoming a smaller and smaller. That is miniaturization of the technology. Initially, we were having the large screen, big box television at our home. Now we have very thin and very thin televisions in our home, and that miniaturization is really amazing. If somebody would have tell you these things, let's say 20 years before, that our television will going to be like a sheet of paper, so that time you people might have laughed at him, because this technology or this miniaturization was only imagined by the scientists, not by the common people. But now the common people, there is a daily use, they are using these kind of the televisions, right? So miniaturization of the device, as I said before, the computer has miniaturized from big room to the small, small case, or like a notebook, right? Small notebook. So this kind of miniaturization happened, and now the next future trend is transparent electronics. So in future, probably you will have the transparent electronics until and unless you switch on the button of your television, people doesn't know whether your television is there on your wall or not. Right? Once you press the button, the television will start, and then only you will understand that there is a television on the wall. Right? So these transparent electronics will be the future. Another is the flexible electronics. If your mobile is a flexible, let's say now the newspapers, we have the normal newspapers, but people are thinking to have these kind of small sheets or transparent sheets, flexible sheets, and where we can just put it on and see the news on that newspaper. That is flexible electronic newspapers probably come into the future. So how this technology had changed, let's have a look here. So the structural engineering, right? The building, functional materials versus advanced materials. And this Moore's law. What Morse was stated is that per square centimeter, every 2 years there will be the double of transistors. So the number of transistors on centimeter square area will double every year. That was decided as a large scale integration of these transistor devices. Later, the technology has switched to the very large integration and then ultra large integration. But now the technology has matured so enough so that we will have the single molecule chip, right? And so that you will have very small and miniaturized devices in your hand. As your mobiles are shrinking day by day and they are becoming very lightweight. So what is the advantage of having this advanced material for this electronic application is the smaller, faster, and cheaper in future. There is almost end of the Moore's law long back, right? And there is how many number of transistors or integrated circuits in per centimeter square? There is 10⁸ to 10⁴, right? So can you imagine how small it is? And it requires very less power. So the power consumption of this kind of electronic devices will be very less, right? So your power saving is another aspect of this kind of miniaturization and the smart technology. And it performs very faster as compared to previously. Previously, when you start your computer, it took few minutes to start up. Now, as soon as you click, immediately your screen opens. So these supercomputers are another thing that which will do the multiple mathematics in a fraction of milliseconds or fraction of nanoseconds, right? So here you see how our brain thinks faster, how the brain speed is. That is 10⁻15 byte of our brain speed is there, right? What about our eyes? As soon as we open the eyes, we can immediately see the images. It means our photoreceptors are 10⁸ times faster, right? So can we reach up to that level, which is already in the nature, right? Okay, let's have a look on these two gentlemen's curves. And these are very important in the nanotechnology, and they are a pioneer of nanotechnology, in fact. So the Louis Pasteur is the gentleman, he stated that the role of infinitely small is infinitely large, right? So if you go at the smaller and smaller level, that role of that infinitely small entity is having the huge potential and infinitely, therefore he's told that infinitely large. Let me show you this gentleman, Professor Richard Feynman, and his quote is very famous, and it is worldwide accepted that he is the pioneer of nanotechnology. The Richard Feynman, his famous quote is, there is a plenty of rooms at the bottom. During the lecture he delivered at annual meeting of American Physical Society in the Caltech in 1959, that time he made this statement, there is a plenty of room at the bottom. So it was his vision, it was his idea, it was his dream that there are a lot of things, if you go at the smaller scale, there are a lot of things, right? So in chemistry perspective, in chemist point of view, he said that if you monitors or if you manipulate the atoms or molecules in a systematic way or a controlled way, you can control the features and you can control the properties of that small scale, right? So it was his vision. So during this talk at Caltech, what this guy has suggested, during his talk, he said this: there is plenty of rooms at the bottom. The miniaturization technology is the future. Synthesis of atoms or molecule control is very important in the future. And after this talk, he had finished this talk with the two challenges. Right? He gave the challenge to the audience that you can miniaturize the page of a text. Let's say we have the textbook, and one page of that text can be reduced 1/120,000 times. 1/120,000 times in a linear mode. So what was his idea is, his idea was, he said that complete Britannica encyclopedia, right? There are n number of books in encyclopedia, or n number of volumes are there, number of books are there. So all those books can we store on the tip of pin. You know, the pin head is very small, right? It is few micrometer or few microns. So that pin of head, can we write all those encyclopedia on the tip? So he said that he announced a $1,000 prize in that meeting, that whoever will do this miniaturization of text or writing of text 1/120,000 times smaller, he will give him $1,000. And second prize was for, he said that building a functional electric motor, but that motor should be very small, right? So we are having motor of some feet or some meter area. So can someone reduce the size of that electric motor by 1/64 time, right? 1/64 time, or 1/64 inch cube. So the small 1/64 cube inch, you have to make the motor, and that motor should work, right? So after this challenge in this Caltech meeting, one of the students, William Macklin, in the Caltech himself, after 1 year, he come up with the nano motor or micro motor, let's say, come up with the micrometer, and he won that $1,000 prize. After 25 years, so it took 25 years to miniaturize the text in really small manner. And you see here in this slide, you see here, this gentleman is Tom Newman. In 1985, he used the electron beam to etch and write this tale of two cities. Okay, one page of tale of two cities on 200 by 200 micron square plastic. You see here the image, and he has written all those things by using the electron beam, and he won the Feynman challenge, and he won the $1,000 prize. Isn't it impressive? So the real nanotechnology has already started by Feynman's vision, Feynman's wisdom, and this Tom Newman has shown him that yes, we can write these things at a very tiny place, right? So this is the beginning of the nanotechnology, we can say. So as this thing achieved by this kind of Tom Wisman, so the change is coming. So from these kind of things, people are sparkle their life, and they say that, okay, oh good, there is change is coming. Earth on the brink. So and after that, you see the molecular manufacturing revolution drastically increase with very low time. But industrial revolution will take a lot of time to transfer this technology from molecular manufacturing to the industrial revolution. So the combinational impact of nanotechnology will equal the industrial revolution of the last 2 centuries. But it all changes compressed into just few years. And now it is rapidly increasing, and 21st century probably will be the wonderful in this kind of real manufacturing or industrial revolution by using these nanomaterials. Okay, so let's have a brief about the nanotechnology history here. So how the nanotechnology has already begun. So there is a debate about these two gentlemen. People have accepted Feynman talk in this APS meeting was startup of the nanotechnology, or he first did the nanotechnology, so therefore he is the pioneer of that, and I quite agree with this statement. But this Norio Taniguchi, the Tokyo Science University person, 1974, he first realized the nanoscale material. He first realized or first synthesized the nanoscale material at laboratories, right? So there is, many people have conflict about this, where Taniguchi is the pioneer of nano or Feynman is the pioneer. But what I feel is, who had generated the idea first and put into in front of everyone, he should give the credit to this kind of pioneering the nanotechnology, right? And in 1980, that Eric Drexel, what he did is, he has done a mechanosynthesis of these nanoparticles. So that is type of top-down approach of 1980 Eric Drexel. So he has invented this top-down approach of mechanosynthesis of these nanomaterials. Then in later 1981, the Binning and Trocher, who has invented the STM. So later on, there are so many prizes owned by these gentlemen, like this C60 invention, STM invention, TM invention, graphene invention, CNT is still waiting to get the Nobel Prize, but sooner or later it may be announced. So these kind of lot of nano Nobel prizes will achieved by these nanotechnologists or material scientists, right? In 1985, the C16, that is a fullerene. Fullerene has been invented. In 1986, AFM, atomic force microscope. In 1987, graphene has invented. Okay, graphene has realized 1987. Let me tell you small about this graphene, because graphene is a very popular material nowadays in all the industries, and it has multiple applications across. And you people might have studied this graphene, right? Graphene is a single sheet of graphite, right? Single sheet taken out from the graphite. So the English chemist name is Benjamin Collin, right? What he did is, he has found first the layered structure of that graphite, and then he found the density of the graphite the first time. It is around 1859, right? Later on, in 1947, this Pierre Wallace, so the Pierre Wallace is another scientist who found out the electronic structure of that graphene, and then he saw the linear dispersion in the graphene, right? But it was not still, this graphene was not given a name as a graphene. They were just thinking about the graphitic structures, and graphitic structure is having the linear nature or a single layer of the graphite, let's say. In 1962, what happened? That Boheman, he first found out the graphite flex. That is the layer of the multi-layer of the graphite. So he gave the name of the graphite flex. But in 1987, the name of that single sheet of the graphite is given graphene, right? It is zero band gap, we can say. Zero band gap, graphene has a zero band gap semi-metallic or metallic nature, and therefore it is very important in different applications. But since 1987, it took how many years to achieve the Nobel Prize? In 2010, we have got the. I'm audible?
Yeah, your screen is not, we cannot see the screen moving ahead.
Screen is not there?
Can you please reshare the screen? It is moving ahead.
Okay, fine. Is it there? Can you see the screen now?
It's not moving ahead, sir.
Okay, fine. I'm going ahead.
It's not moving ahead.
Yeah, sure.
Yeah, please reshare the screen.
Now it's fine? Is it moving?
Just a minute. Yes.
Yeah. Now it's working, right?
Thank you, please.
Yeah, fine. Sorry for the inconvenience. Okay, so let's have a look on 1991. The Japanese Professor Ichima, who has synthesized the carbon nanotubes first, CNT. Let's have a look. This is just cartoon. I would like to give you the feel about where the interface is. If the nano is just everything on the surface, all the atoms are the surface atoms, then where is your interface, right? So the atomic sandwich making is the art of this kind of nanotechnological work, right? So this is just to give the feel. Do you know where your interface is? And to finding those interfaces is very difficult in case of the nanoscale. Okay, so this is a very general slide, and I think most of the student will get a feel about how the nano is very important. So let's have a look on this slide. What are the nanoscale particles, right? So in what regime we can say these are the nanoscale particles? You see here the atoms and molecules. Okay, let's say only single atom or single molecule is there, and it falls in the quantum chemistry, right, or quantum physics, let's say. In the condensed matter, 6 into 10 raised to 6 number of atoms or molecules are there. So n raised to 0 atoms, and it will be around more than 100 nanometers, and it falls into the solid state physics. That is the bulk phenomenon of your material, right? But in this nanoscale particle, you see 125 to 70,000 particles together may form 1 to 10 nanometer of this length. And will it fall into the nanoscale? So can we make the definition? You see that in many books, in many nanotechnology books, you see this less than 100 nanometer is treated as real nanoscale. But is it the correct definition? That I will come in a minute to that explanation. Okay, but what is the importance of having this nanoscale is, you see here, the nanoscale metallic particle, initially this is the bulk particle. Then you see here, you can break into the pieces, and again you can break into and go to the molecular level, right? So chemical and physical properties of this kind of nanoscale is an intermediate between your bulk and molecular cluster, right? And these properties are affected by the large fraction of surface atoms. It is affected by the morphology, it is affected by the electronic structure, because there is a quantum confinement of the charges into this small structures. So what about the surface area? All the time we heard about the nanomaterials have huge surface to volume ratio. What it means, surface to volume ratio? You see here, there is one crystal, okay? There are total number of atoms are 4,096, and surface atoms are 1,352. So if you cut this crystal into 8 pieces, you will see that total number of atoms are the same, because the same crystal you have break into the 8, but the total number of surface atoms which are situated on the surface, will be 2,368, because we are considering each surface atom of those all 8 cubes, right? Again, you convert this 8 multiple into 8, right? So total 64 cubes, right? Break into the 64 cubes, and you will find out the total number of atoms are the same, but the surface atoms are increased drastically, right? So if you are cutting into the nano pieces, you will find out large number of atoms.
Hello,
He is not audible.
sir. We are not getting your voice.
Volume, let's say if in this volume there are thousands of atoms, and most of those atoms okay, can you hear?
Yes, sir. Yes, sir.
Yes, please go ahead.
So here you see these 2 different approaches to synthesize those kind of nanoparticles at the nanoscale. Okay. So what are those 2 approaches is? One is bottom up, right? And then
Sir, your
top down
sound
is
is
you take the
getting
bulk part, break into the small.
Your sound is getting interrupted.
Okay, now I think it's hearable, right? I'm audible?
Yes. Yes, you are audible, but it is getting interrupted.
I see. Okay, let me check. Yeah, fine. So here, it's fine, right?
Yes, please.
Yeah, can you hear me now?
Yes, sir, please go ahead.
Okay, so there are the 2 approaches to synthesize those nanomaterials. One is bottom up, attach one atom by atom and form the nanostructure, or you take the bulk material, break into the smaller pieces and make a tiny nanomaterials, right? Here you see, these are the different nanostructures which has been already synthesized in my laboratory by my PhD student Shobhnath Gupta and other students. So here you see, these are the beautiful nanostructures. This WO3 flower, at 1 micron, you see one flower is around 1 micron and there are a lot of number of small petals. And all these materials have been synthesized by a chemical method, right? It means it is a self-assembled chemical method where we have attached atom by atom and form this kind of the different structures of different materials. Let's say WO3, then MOS2, then MnO2, black phosphorus, and these are another materials like nanofibers. We have the nanobelts, twisted graphene ropes, and CNO flowers. So all these things has been generated by bottom-up method, right? Which is the simple chemical method. We have generated all these kind of nanostructures in the lab. But what about the top-down approach that I'm going to show you in a minute? As we go ahead, we'll see that top-down approach as well. Okay, so what is the definition? Just now I said the definition is the important parameter. So many people said that less than 100 nanometer is the nanoscale. But what is accepted by the scientific community is that if the properties of your bulk material start changing, right? At the level, let's say some materials will start changing its property at 10 nanometer onwards, okay, less than 10 nanometer onwards. Some materials will show the property changing less than 50 nanometers, right? Some materials will show the property changing after 200 nanometers. So when the property started changing from bulk to the bulk, that regime is called as a nano regime. And below that level, you can treat those materials as the nanomaterials, right? So it's not like only 100 nanometer is the final limit. That limit can be shifted upward and lower directions, right? So this is the proper definition of the nanomaterials, right? So scaling up or down with the size, and again the size and shape are a lot of the parameters which can change the orientation of your atoms, arrangements into nanomaterials, and which will also tune the properties. So how that is happening, that we'll see in a minute, right? So there are some illustrative examples. Here in this slide, you see there are the two examples here. As you reduce the melting point, right? So you see here the melting point of AUAG and bandgap of semiconductor bandgap engineering. So you see here, if you reduce the diameter less than, let's say, 12 nanometer or 10 nanometer, your bandgap is starting opening, right? So if you are reducing the size of nanomaterial, the bandgap is going to open and bandgap of those materials are increasing. Here AUAG we have used, and let's see the melting point and particle size radius. So if you are reducing the particle radius, you will find out the melting point drastically changes, right? So at this regime, let's say 10 nanometer or 12 nanometer is the limit of where you can find the nanomaterial properties of those particular materials. Let's have a look at these beautiful examples with respect to shape and size, how the properties of these nanomaterials are changing. Here you see the A figure, which is AU nanoprism, gold nanoprisms are there, right? These are AU nanorods, B, where you see the nanorods are here. And then this is silver AG nanoprisms, prism-like structures, three-dimensional prism-like structures. So here you see in the D, we have AU and AG combination, right? Gold and silver nanoparticle alloys. Okay, if we increase the concentration of gold little bit, if we start increasing the gold contribution, we will see here the change in color is observed. Why this change in color observed? Because bandgap has been tuned, right? And therefore there is a change in color as observed. Similarly, without adding anything, simply you see these are the gold nanorods. And if you change the gold nanorods aspect ratio, what do you mean by the aspect ratio? Is length and diameter ratio, right? So if you are increasing the length of these nanorods, you will find out there is drastically change in color. So if you start increasing the aspect ratio, you will find out the color is tuned, right? So it means the size also matters a lot in case of this nanomaterial. So this is very beautiful and fancy science where your size, shape, orientations, and so many things will play a crucial role. And therefore, studying this kind of nanomaterials is a real art, right? If you have the artistic mind, you will enjoy working on the nanomaterials, right? Here, these nanoprisms with size change. If you increase the size of this, you will see there is a change in color, right? Size of the prism. So these all has taken from the Materials Today journal. If you want, you can go and see that paper. for more detail about this, how this nanomaterials property can be tuned by changing its shape, size, and composition or alloys concentration, right? So this is the very beauty of nanomaterials. Let's have a look on another thing, this gold nanoparticle with different sides. So usually we know the gold is having yellow in color, right? But here you see in this another figure, this Michael Faraday, what he has done is colloidal gold preparation he made, right, in around mid-80s, right? And the mere variation in the size of the particle gave us the variety of the resultant colors. So in 1800s, mid-1800s, Michael Faraday was invented colloidal gold. So it means that it was already there, and this invention, but people have rigorously studied all those properties of the nanomaterials later, and they have found out these beautiful, fantastic properties of the different material as well, right? So this gold nanoparticle of the different size, you see, if you change the size, the color is definitely changing, but advantage of the gold is, you see the gold, if we go at the nanoscale, it shows the good medical properties, medicinal properties. Therefore, this nano gold has been used in medicine widely. Okay, but bulk gold is not useful for this kind of applications, right? So here you see in the fluorescence as well, the CDSC nanoparticle with a different size. So band gap, ultimately there is a band gap difference if you are changing these colors. Ultimately there is a band gap difference, right? Okay, let's have a look on this beautiful nanomaterials or nanoparticle example, which was there since fourth century. Okay, and this is Lysager's cup, and this Lysager's cup is called as a Roman glass cage cup, right? And you see the color of that cup is changing. So what it means, what the Roman glass is made up of, right? So those Roman glass are made up of gold nanoparticles in that, gold and other nanoparticle composites is there. And so these composites are helping us to understand why these properties are there. You see here, the color is changing. So what happens if you put a light inside the glass, right? Then red color, you are seeing the red color when you are putting light inside the glass, and the transmitted lights come into your eyes. So the red color will give by the transmitted light, right? But this green color is given by reflected light. If you shine a light from outside, you will see the green color. If you put the light inside the cup, you will see the red color, right? So similar kind of things are there, and then later people have invented why this kind of miracle happened in this kind of Roman glasses, because these Roman glasses were made up of composite of the nanoparticles or alloys of the nanomaterials, gold and silver, gold and copper. So these kind of different combination of nanomaterials give you the effect of this kind of different colors, right? If you go to the church, you will see there are the different glasses. I will show you the example of our own university. You see here, this is our Jahangir Convocation Hall of the University of Mumbai. I hope that many of you might visited this hall before, right? As it is owned by our own university, and UNESCO has announced, or UNESCO has awarded this as a heritage conservation, right? Awarded for the heritage conservation of this hall. And you see here the upper dome, which is having different glasses here, right? And those different glasses, you see beautiful colors inside those glasses. So what those colors are? So these are the Roman glasses, and in those colors there are nano composites or nano alloys are there, right? So if you change the size of the nanoparticle, ultimately band gap changes and it gives you the different colors. So if light is shining from the outside, you will see the different color, and at the night probably you will see the different color if light shines from the inside, right? Another example of our own university, you see here the library. We have the reading hall of our library at Fort Campus, and in that Fort Campus you see these glasses, the beautiful colors, right? So daytime you see the different color, at night time you see different colors, and these all are made up of the fancy of nanomaterials. So you get me? So I hope you people, if you are having any question in between, you can type in that, so that probably I will focus on those questions and try to elaborate more immediately at the same time. Okay. Okay, so let's see another example of what were there in nature, because this all materials, what the advanced material we are talking, all the novel materials we are talking, everything was there in the nature. Everything is there in nature. We are just exploring it out, right? So here you see the color changing materials. There are photochromic materials, there are electrochromic materials, there are thermochromic materials. So these are the different class of materials are existed there. So what are the God's own nanomaterials? You just have a look on this. You see here this peacock, and you see here these peacocks. Here you find the different colors. So these beautiful colors are arranged because of this nano arrangement of that pieces, right? So how that nano arrangement of pieces happens, if you take out a piece and put under the microscope, you will see what is the beautiful arrangement of that kind of things. And because of the specific arrangement of atoms at the nanoscale, you see these kind of beautiful colors, right? So similar thing is happening, you know the champion who are, champion who are changing the color changing champion, right? If you go into the forest, it change the color. If you come into the, so these things, color changing materials are always there, and you find out nanotechnology or nanomaterials are playing a role. If you know the nanomaterials, you can easily understand how this behaves like, right? So let's have a look on another thing. Most important is molecules as electronic components. So here you see this is called CNT, and you have the STM chip on that. If you apply the little bit of voltage, what is happening here? The movement is happening without touching to that nanotubes, right? So it is opening the channel like our pumping the heart, right? Same thing is happening. So there is electron channel which can be tuned by the external electric fields. So you can monitor or you can tune properties of your transistors or your electronic devices by applying a very little amount of voltage, right? So at nanoscale, you can control the flow of electrons, right? And therefore, you can control the speed of your electronics as well, right? So this will be very helpful. So what this scientist has, William Beck, what he said is, after seeing all the previous examples, the art and science could exist only in a minute particulars, right? So if you know the science, or if you have the basic knowledge about the science, if you have the artistic minds, then you will have good fun with this material science and nanotechnology. Same thing William Beck has highlighted over here. So let's have an example about the nature's own nanomaterials, that is a self-assembly and biomineralizations. So you see here the seashell, a protein aragonite scaffolding, right? So that is very hard, very tough on the surface, and same time you see it is very polished and very hard. Why did it become very hard? What is behind that? So if you go and see, if you break it and put it under the electronic microscope, you will find out the arrangement of atoms having the specific orientations, right? And that arrangement make them very hard. Same thing if you go and see the spider silk, how that looks like I will show you in the next slide about the spider silk. Similarly, you can see the magnetotactic bacteria, which can orient and migrate along the geomagnetic fields, right? Here, these are the bacteria and at geomagnetic fields, which can orient and migrate in that particular direction. And here you see the spider, right? Spidemex, what the Spidemex is? Bio-inspired material like things, right? So let's have a look on this spider silk. You see here the spider silk, an amazing material. Spider silk, we see it's very lightweight, right? But if you try to break it, it won't break. It is flexible, but it won't break. Why it doesn't break? It's very strong, 5 times as strong as the steel, right? It's stretching 30% before the breaking. So their stretchability is there, flexibility is there, and stronger than the steel. And you see here, this is the spider silk. If you see the structure of spider silk, this kind of stacking arrangement is there in that. And this stacking arrangement makes it very strong, right? Very strong and flexible at the same time, right? So these are the natural's own nanomaterials available around us. We have to just go and explore those materials. We'll find out the beauty of those materials, and then we can replicate. That is, biomimic is the another area where people are thinking, people are going into the nature, see the materials, and try to replicate those materials in the laboratory. So that is a good area. Many nanotechnologists are trying to manufacture similar kind of nanomaterials in the lab, right? They study first this natural structuring, and they try to replicate those structures in the lab, and they try to find out such kind of very hard, strong, and flexible and stretchable materials at nanoscale. Similarly, you see here the super tough natural composite, and you see what is the arrangement, how the key lock arrangement arrangement or stacking arrangement is there in this kind, and therefore it become a very hard. Okay, I hope you understood how the nature is helping us to explore these novel materials. Let's see here the bio-inspired material like a Spidey and Spidey net you have seen, right? So let's compare this Spidey with other things. Let's say you have the Kevlar and you have the rubber and you have the tendon. So the strength of this Spidey and energy to break. So energy to break this Spidey silk, spider silk is very high. Required energy to break is very high. Strength is also very high as compared to your rubber, tendon, and Kevlar, right? So this is the beauty of these kind of materials, and which similar materials we can replicate in the laboratory. Okay. Okay, let's have another thing, the nanotechnology, which is making super hydrophobic skating. You see here, this is the natural super hydrophobic leaf, right? That is lotus leaf, where you see if you drop the water on that surface, it won't stick to that. It will simply slide and it will become hydrophobic because its contact angle is more than 150 degrees. But why it is happening, if you go to the nanoscale or microscale, and if you see the image, you see this is the morphology of that surface of this sheet, right? Surface of this leaf, you see the morphology of this, and this water droplet is there. So they are not allowing these kind of structures, small hairs are there, and which are not allowing your water molecule to stick on that. So the surface tension phenomena comes into picture, and therefore this drop gets sliced over these kind of rolls, and then ultimately it goes off. It falls down to the surface, right? And therefore, this idea from these kind of surfaces, scientists got an idea about the self-cleaning materials or self-cleaning property of the materials. So scientists try to find out the self-cleaning material by using, let's say here, using the silica or OTS sands, right? So this super hydrophobic material development has encouraged or get motivated by seeing these kind of surfaces available in the nature. So I will show you the small video where you can see the hydrophobic materials using the nanomaterials. You see here, this is the small video. So you see here, this is uncoated area, and here is the coated area. Definitely there is self-cleaning materials. You see, at this coated area, you won't find these water drops get stick more as compared to this one. So it is a self-cleaning area. Right? So this is the self-cleaning area. Okay. So that was the self-cleaning area, right? So which was usually made by the TiO2, right? So TiO2 is is created as a self-cleaning material. And usually what happened, the heritage buildings are coated by such kind of nanomaterials or nano paints nowadays are available, so that can be coated to your building. And these kind of water droplets cannot stop on your building, so that there is no fungal growth, no antibacterial, bacteria grown on that wall, and therefore it is a get protected, right? Okay, so let's have a look on this kind of silent feature. CNT is another popular nanomaterials, and you see the silent feature of those, right? How this hexagonal sheet of graphene will roll and form this kind of single wall nanotubes. Then there are a number of layers of the graphene rolled over and form the multi-wall carbon nanotubes. So what is silent feature of this CNTs are fundamental quantum confinement physics, extreme mechanical strength and flexibility. It can be used for various applications like nanoelectronics, hydrogen storage, gas sensors, SPM, nanoscale actuator, device display, and number of applications of this CNT. But here, what is the importance of having this carbon? Let's say we have the different ordered carbon structures, right? So we all know about the graphite. Graphite is the stack of graphene sheets. But you see, the graphite is very brittle at one side, and another side, the diamond is also made up of the carbon, but diamond is very hard and tough. So why it is so? It's just because of arrangement of the atom in a particular fashion, right? That is a structure. So structure plays a very important role. And similarly, this carbon atomic arrangement has found in n number of allotropes. You can find a lot of allotropes just by changing the alignment of your atoms. And you see here the C60. is fullerene, like football type of balls arranged by number of carbon atoms, and hexagon and pentagon rings has formed this kind of C60 atom, which got the Nobel Prize, right? Let's have a look on C70. Just at the center, you just replace those atoms, right? Hexagon, pentagon, and then CNT just roll the graphene sheets and form the tube-like structures. So carbon nanotubes are as strong as the steel, or much more than the steel, and very lighter than the plastic. So these CNTs can replicate those spider silk, what I showed just before. So can these CNTs replace those spider silk kind of structures, right? So I would like to show you this beautiful slide. What this scientist who has in buckyball product, right? So Buckminster Fuller, what he said is, we are called to be the architect of our future, not its victim. So I appeal all of you that just to enroll in the science and nanotechnology and try to find out or try to create some miracles rather than you try to architect the future by using these nanomaterials. And I hope you all people will get motivated through this kind of fancy tour of nanomaterials, and you will understand. You see here the Richard Smelly, what he said is, we'd like to make it in a continuous fiber, roll it on drum, and go for fishing. So it means if you roll the, let's say if you roll the CNTs on the drum, right, because it is very strong than the steel and very lighter than the plastic, so it can easily float on the water, right? So you can just, right, put it into the water, so it will float on the water, and you can go for the fishing. So this is fantastic idea was created by the Richard Smelly, right? Okay, so how the CNTs are playing a major role in electronics, especially. You see here, it can conduct very high current, right? And there you find out the current and voltage, that is a single electron transfer. Okay, here one electron, another electron, another electron. So one electron by electron. So there is a control of flow of electrons by single electron. So you can control flow of electron one by one electron, right? And then another importance of this CNT is that it can handle a very high current densities. Therefore, it becomes very faster and smaller. Cheap contacts, you can use this CNT, right? But it may have the contact problems, and that can be solved by nanomaterials as well, right? Okay, and then another thing, as we have seen, there are so many nanomaterials, so many things are available, but manipulating it at nanoscale is very tough job, right? And here, this IBM scientist, okay, what they use is, they use the STM, right? And they use Xe atoms on nickel surface, right? And they have arranged the atom by atom in a such fashion that they can write an IBM at a nanoscale. So it means you can mechanically move the atom by atom and arrange in a fashion as you want, right? So this is very fancy thing that STM had shown to the nature, right? And then what Richard Smelly said, just wait for the 21st century. It's going to be incredible. We are now in 21st century. We are about to be able to build things that work on the smaller possible length scale, that is atom by atom. And here in 1990s, that was already done by the IBM. But now, still onwards in this 21st century, we will find more miracles in this, right? So these nano things will revolutionize industries and our lives, and we are going to see more. So let me go to this top-down approach. As we were discussed about the bottom-up approach previously. What is the top-down approach? You have to break some things into the small pieces, or you can write something on that, right? And this work has done in our laboratory by Dr. Suhas Jezurikar and his students. What they have done is, I will show you a little bit. But here, what is so prestigious about human is hair, right? Without hair or face, and our beauty will go off. So this hair is very important, right? So what is the size of hair? Hair is 1 lakh times bigger than the nano, right? So 1 lakh times nano. And here you see this is human hair SEM image, which is around less than 80 micron, right? Let's go here. Let's look at the atom. So you use this STM to look at the atom, and you find out this is the HOPG image, atomic arrangement, hexagonal arrangement of these carbon atoms. And you can reach up to real mapping of the atomic structure. As we see previously in the IBM lab, they have arranged it. We have here just only mapped the structure of this HOPG at the atomic level. But what here is typically the STM team Here you see the tungsten tip actually. This tungsten tip is very sharp and which has very few number of atoms on its tip. Therefore, it will be easy for you to slide on the surface and map your structure. Now let's see here in this tip, you won't find anything. Can we write something on our hair? Let's say if I suggest that you write your name on your hair. Is it possible? Yes, obviously. Because Tom Newman in 1985, he has wrote complete textbook in, let's say, 200 by 200 micron area. So why don't we write our name on our hair, right? So that is quite possible by electron beam, you can write on your hair. So let's have a look. What we have wrote on this is this. Here you see, this is the tip, and here in this region, you see there is something. We have carved something in that. Let's zoom it further. Let's zoom it more. Let's zoom it. You will see something there. Oh, man. So now you see, what is this? This is nothing but our Rajabai Tower of University of Mumbai, right? And three-dimensional Rajabai Tower has been carved on this. And you see this SEM image of this Rajabai Tower, right? So this three-dimensional carving or writing on this tungsten tip, you know, usually the tungsten is very hard to write on. It's very hard material. It's very difficult to carve on. And after many trials, we were able to do this kind of carving in this tungsten tip. So this is the top-down approach. You know, you have to take a bigger things and write smaller. So how it helps us in the future? Let's say in security point of view, if we do this kind of mapping or labeling or stamping on mapping and stamping on the, let's say, notes. We have the notes and we don't know those notes are original or not, right? So it's very difficult to identify. So in that case, what you do is you can carve such kind of symbols on those notes and which can be visible under the microscope, right? So as soon as you put your currency under the microscope, you will see whether the hallmark is there or not. And then you can decide whether it is an authenticator, right? So for the security purpose, this kind of technology will be very helpful. Okay, let's have a look on material responding to change in environment. That is a super material. Probably you see here, there are the different application of those materials, smart materials, where the sensitivity, shapeability, self-recovery, switchability, self-repair, selectivity, self-diagnosis, there are so many things that smart materials can play a role in, right? So what is the smart versus stupid materials? What do you mean? The smart materials have the multiple functions at a time, right? And these smart materials can be classified in passively way, actively way, and very smart way, right? So there are different examples of the smart tennis rackets, smart carports, smart toilets. So these are all made up of the nanomaterials. Therefore, they become a very smart, they show the efficiency, right? Okay, so let me go to another thing, smart polymer gel. So there are so many good examples around here. So I will try to have a tour of all those examples in next half an hour. So that, you know, we will have enough understanding about this now, right? So this smart polymeric gel, you see here, the 3D polymeric network, which reversibly swells, right? So reversible swelling of these polymeric gels with respect to temperature, your pH, then you find the ionic strength, electric field, then light and solvent and enzymic concentrations, right? So here you see, if you apply this, E is equal to 0 and E is not equal to 0, what will happen? You see the level and there is, you know, there is gel sections here around, right? So these microgels get the reversible, there is expansion and contraction, expansion and contraction. If you give the temperature, probably let's say it expands. If you reduce the temperature or decrease the temperature, it will come back to its original position, right? So it can act as actuators. You know, in actuators, usually we can use such kind of polymers and things. Okay, let's have the artificial muscle. Can we make the artificial muscles by using this nano network? This is the nano networks or the smart polymeric gels where it can function, right? So this is the another example of the artificial muscles. Let me show you the electrorheological fluids, right? So electrorheological fluids are another important factors. So viscosity variation with electric field, switching in milliseconds, just a milliseconds. You have to just change the electric field, you will find out the viscosity will change of these particular gels, right? So microscopic particles in insulating liquid. So these microscopic particles will be playing very important role under the electric field, and therefore there is a change in viscosity will happen, right? So the ferrofluids, we know the ferrofluids, you have to just apply the magnetic field and you will find out the ferrofluids, fluidic moments will happen in the direction of the applied field, right? So what are the application of those materials is that electrorheological clutch, adaptive shock absorbers, optical switches, right? Or shutters, then magnetic inks. These are the various applications of electrorheological body self-diagnostic composites. Also, these materials can be used. So this nanotechnology, which can use to make the smart materials. You see the ferrofluid is a liquid which strongly polarized in presence of magnetic field. So ferrofluid are composed of a nanoscale ferromagnetic particles which are suspended in the solvent and water, right? If you apply the magnet, let's say, and give the direction, it will move in the direction of that applied magnetic field, right? And another thing is, if you functionalize those ferromagnetic materials to any other nanoparticles, those nanoparticle agglomeration won't happen, right? So to make these separated nanoparticle or suspended nanoparticle, sometimes people use the ferromagnetic nanoparticle coatings, ferromagnetic nanoparticle composites, right? So what are these liquid magnet applications? So this liquid magnet application is ink, money ink, right? If you are using the pen, and that pen should not agglomerate at one stage, right? Therefore, this coating of the nanoparticles, magnetic nanoparticle is required. In biomedical case, what happens if your nanoparticles are going inside the body, there is a chances to agglomerate these nanoparticles, and accumulate in the body somewhere, and it may cause the cancer. So there is a huge problem if there is agglomeration of nanoparticle inside the body. So if you have the ferromagnetic nanocoatings or nanocomposites, then the agglomeration of the particles inside the body won't happen, right? So then another thing is the damping, the speaker, graffiti plotters. Then fourth one is the seals like a gas lasers, motors, and these are the n number of applications of this kind of the smart materials, right? Okay, so can we find out the smart nose, like it's artificial olfactions, right? So you see here, these kind of nanos which are having very high sensitivity, when very less amount of gases exposed or very less amount of gases come out, it has a capacity to go at ppb level, parts per billion, parts per million level, to detect those kind of the gases, right? And within a milliseconds or nanoseconds. So these are the very smart nose or smart sensors we can develop by using the nanomaterials. There are n number of sensors which we can make. Shape memory alloy, I'll just keep this electroceramic, probably I don't want to go much into this. And we can develop these resistance changing materials like ZNO varistors. We will have the different properties with respect to voltage resistance, voltage temperature by using this BATIO3, ZNO, right? So these are the resistance changing materials we can develop by using the nano. So let's have some fancy example of the future, what people are doing at the moment using this kind of nanomaterials, and what sort of things people are trying to do with nanomaterials. So here is one research paper we have collaboratively published with Dr. Ankush Birazdar, who is the scientist at CSIR Bhavnagar. So what we have done is, you see here, this is sugarcane farm, right? So this sugarcane farm, there is a biomass. We have taken that sugarcane, right? And that sugarcane we have burnt, and we have taken a carbon from that. And those carbon we will use with other precursors and do the hydrothermal treatment. And then finally we find out the silica-free precursors, right? And these silica-free precursors are showing active organocatalyst, right? So this silica free precursor shows the organocatalytic properties. So it means you have the biomasses, right? You can convert those biomasses into the beautiful nanomaterials, right? And those nanomaterials can have the applications into your scientific need or technological need, right? So from environment to the technological need, right? Okay, let's have another example here. This is another fancy example. So this is the integrated device of generation of electricity using the CO2 and generation of hydrogen. So this is very beautiful concept. Professor Kim in School of Energy and Chemical Sciences, right? Chemical Engineering at UniST, in collaboration with Cho in the Department of Energy Engineering and Professor Lee in material science, Georgia Tech University. What they have done is they have put a concept that can we take this CO2 which has emitted through these plants, right? Industries, huge smoke is coming out. There is huge CO2 there. Can we take those CO2 and dissolve it into this kind of cells, right? Dissolve it into these cells, aqueous electrolytes, and you can generate the hydrogen. At the same time, you can give the electron, that is oxygens, or H plus going here. You are finding out there is another electron, and here there is a, let's say, energy storage device, right? So this is battery or supercapacitor or galvanic cell. Here you can just dissolve the CO2 into that, produce the hydrogen, and same time store the electricity or produce the electricity. So this is very beautiful technique, integrated device, and future technology will be using these kind of things. And here these cathodes and these electrodes will be made up of this nanomaterials. So if you use this nanomaterial cathode or nanomaterial storage of energy, that is for autos and all, or generation of the electricity which can be utilized for other applications. So three things are solved by the single device. So this is the potential and beauty of these nanomaterials, right? Let's have a look on another very important thing, another important device, integrated device, of course. Here you have one device here, another device here, right? One device is you just put a light on this surface, right? Here there is a PN junction, like solar cells. You generate the electricity. Same time, here is the electrolyte which will absorb the light, and there is a storage of energy here. So in same device, you have the generation of electricity as well as the storage of electricity in this device, right? And this work has done in a Berkeley lab, right? So two devices in the same time, and which will be controlled or which will be operated under the sun. So you are using the sun energy to generate the electricity and to store the electricity as well. So these are the beautiful examples. Currently, people are working on this. I would like to show you the important thing about this energy and how the nanotechnology is playing a role. You see this Bucky paper, which is unlocking power to nanotechnology. Very small video, you just have a look at it. Okay, so hope you enjoyed this video and you understood about, am I audible? Hello?
Yes, sir. Yes, sir.
Okay, so hope you enjoyed the video and you understood the importance of these nanomaterials, how it improve the efficiency and how you reduce the weight of any appliances, and then how it will be useful to increase the efficiency and save the power as well, right? Another important application of this nano is clean water. And there is a very big institute of the clean water in IIT Madras, headed by Professor T. where they have worked on a variety of nanomaterials which will be used to purify the water, right? So to remove the contaminants or arsenics from arsenic from the water and make it more drinkable water by using these nanomaterials or nano mesh, right? Nowadays, in aquashear technology, you see nano RO, where they use the nano membranes or nano filters using the silver nanoparticles, and they try to make a clean water. So this is another very big area where the nanotechnology or nanomaterials are playing huge role, especially those silver nanoparticles, TiO2, zinc oxides, so many nanoparticles which are playing huge role in cleaning the waters nowadays. Okay, so the very important thing why we are here today in the virtually we are having this kind of webinar is because of COVID, right? But for the COVID, now nanotechnology will give a better solution, and therefore whole world is eagerly looking towards the nanotechnologies and nanoscientists to won the battle against COVID-19 by using the nanotechnology opens, right? So in this COVID, there are three important things need to be done. First one is the protective kits. Those doctors, they are treating the patients. They need very highly protective kits, right? PPE kits, and normal people, they need masks, which will be the antiviral masks so that your corona or COVID-19 virus will not affect the normal citizens. Another thing is sanitizers and detergents to kill those viruses. So that sanitizers and detergents can also use the nano emulsions or surfactants at the nanoscale. Then ultimately the medicine. So nanomedicine is another huge area where people are trying to use this nanomaterials or nano treatments to find vaccines and medicines, right? So recently DST has focused on nanotechnology and they have announced several funding schemes where the nanotechnologists can enroll to fight against this COVID-19, right? So here I would like to show you some of the examples what people are doing, especially in India, to tackle or to defend or to face this kind of pandemic situation and conquer the war against this COVID-19. So you see here the IIT Roper, what they have done is they have prepared these nanofibers, right? So they have prepared these nanofibers, and these nanofibers will be coated on your mask or PPE kits, right? And these nanofibers are antimicrobial and antiviral. They are antimicrobial and antibacterial activities, and so they will protect you from this 19. So this is the recent development of IIT Roper. I would like to show you another recent paper, the ACS Nano recently published in last month, where what people have done is they have prepared this mask using graphene, and they have used the you see the title here, the reusable and recyclable graphene mask with an outstanding super hydrophobic and photothermal performance. See this COVID-19, right? So this coronavirus will stay longer in this kind of moisture conditions, right? So therefore you need the super hydrophobic properties of your mask, number one. Number two, the photothermal performance is as soon as light incident on your mask, it will heat it up and it will try to kill those kind of the viruses, right? So this kind of fuel layer graphene coating has done on the mask, and this is already published in ACS Nano recently. So why I'm showing this is just I want to showcase the potential of nanomaterials to tackle such kind of situations or take up the challenges of the society and go further, right? So let's have a look. These are the NCL who developed the face mask capable of filtering 99% of bacteria. The Dr. Mahesh Darne, who is collaborator of our working in NCL CSIM, and they have developed, their team has developed this cotton cloth coated in the solution of bacterial cell leaders and nanomaterial, which can prevent the bacterial growth, right? Indicating a promising material for the face mask. Another discovery happened in our Mumbai University itself. Dr. Vishwanath Patil from the Department of Chemistry, he recently made this kind of polymeric coating embedded nanomaterials. Right? So nanomaterial embedded in the polymer matrix, and this coating will help you to kill these viruses or prevent you from the viruses. And this is very good invention, and it is under a trial for the antiviral testings. So this kind of nanotechnological applications around us, and in India especially, because abroad we know a lot of people are working on this kind of area and they come up with the discoveries, but Indian science also has a huge potential to take over or take up these challenges and tackle these situations, right? And since we are in Mumbai and Pune like city, we have huge infrastructures, and our nanotechnology is also playing a role to tackle such kind of situations. We are also developing so many materials in our laboratories, and we have submitted so many proposals for the DST and other funding agencies to make such kind of coatings and such kind of fibers for PPE kits and all those stuff. So another thing is in the vaccine, so gold containing drug, auranofin, kills 95% of SARS-CoV virus in 48 hours in the labs conditions. Okay, this news is published here in newsmedia.net. So you can go and explore about how this gold containing drug will be helpful for this COVID-19, right? But let's have a look in Indian scenario, the Kolkata Institute, which claims to cure the COVID-19, right? And Dr. Samir Pal is the professor of Institute Department of Chemical, Biological and Macromolecular Sciences and former professor of California Institute of Technology, has developed such kind of nanomedicine which can take up the COVID, and it is under trial. So this nanotechnology, people are eagerly looking forward to the nanotechnology decisions to solve this kind of pandemic situations, right? So nanotechnologies means it is an interdisciplinary field where all chemists, physics, biologists, engineers, they all involve, and their team will work as a nano scientist or nanotechnologist, right? So these are the different medical applications where nanotechnology can play a role. One is research and another is direct clinical trials. First one is drug screening can happen at the research level, then direct drug delivery in the clinic can happen because of these nanotechnological evolutions. Then gene delivery can happen in the research, and the detection can be found out. So see, the nano sensors are also playing a very important role, because very small sample, with a little sample, they will find out the correct measures or correct diagnostic can be done by using the nanomaterial because of their efficiency and smart materials, right? So this diagnosis is the area where a lot of people try to find out the nanomaterials for these diagnostics, right? And a lot of medical devices nowadays, they use the nanotechnological fabrication tools so that they can use those nanotechnology to find out the diagnostic kits, right? And smart diagnostic even within a short span of time you will get the correct results, right? And with a good efficiency. So this is the potential of this nano for the medical applications, right? So let us have another video which will give you the glimpse, I think. Okay, so that is not working at the moment, but it's supposed to show you what are the importance of these biomedical applications anyway. Okay, so what are the benefits and risks about the nanotechnology. We have seen, there are so many applications of nano, lot of potential. There are n number of smart materials, n number of materials has been created at the nano scale. The properties has been changed. We can use a bottom-up approach, top-down approach to prepare the nanomaterials. So a lot of things we have seen, but we need to really judge about what are the benefits and what are the risks involved in this kind of nanotechnological work, right? So an automated self-containing factory could provide this kind of benefits and risks. So life-saving medicals, we can have the life-saving medicals by using this nanotechnology. We can have the robots which can go into your body and repair or repair your body by itself. You need not to go to the doctor. As soon as it gets indication that there is a blockage in your inside the body, then immediately that robot will go there and remove the blockage. So that kind of nano robots in future probably we are expecting that will come and they will repair itself in your body, right? But what is the risk is untraceable weapon of mass destruction, right? So similar robots, let's say if some enemy can create such kind of robots and send in your body and create problems. So that is the risk. Another thing is, what are the benefits? Networking computers for everyone in the world. We will have the good networking computers by it. But the network camera, so the government can watch everyone's move, right? So this is the technological problems or risk in future. $1 trillion of abundance is the benefit. But what is the risk is? A vicious camel to own everything, right? And rapid invention of wondrous products, but the risk is weapon developed faster enough to destabilize any armor races. So this is, just I will try to give you flavor about what are the benefits and what are the risks of this technology maturing or technology advances, right? So let's forecast for the future. What is the future of this nano? Right? Future of this nanotechnology. We know the nanotechnology can be utilized each and every place. In future, everywhere you will find the nanotechnological contributions, since from your medicine to your technology, right, to your engineering, medicine, and everywhere, you will find out the nanotechnology contribution. But you see the forecast for the future. We can go to the cashless economy. Let's have the voice-driven furniture. If you have the smart voice recognition devices, and same time you will have the actuator. If you speak, whatever they will take your orders and they will work accordingly like robots. So we have voice-driven furnitures. Web-based control over the transportation. So what you do is, just now we are doing this kind of Ola and Uber booking. So in future, if there is a driverless cars, you have to put the destination online that, I want to go from Palghar to Mumbai. You give the destinations and then that self-driving car will take your kid or somebody from your family from Palghar to the Mumbai, right? So automated payrolls, defective gene replacements. So, if there is a genes are defective, then that can be the biomedical or bio-nanotechnological growth. Collision avoidance system is another forecast for the future. Confession to artificial intelligence. So AI nowadays, is a very important, and nanotechnology jobs and made very easier by this AI. So AI will help you to reduce the experimental time and go into the precise one. So this AI is coming, along with nanotechnology, 21st century will be with AI, right? So designing babies, as we have this VFC and all those things. So insect like robots for the crop pollination, right? 2012, and that will happen in future also. So ID card replaced by biometric scanning, that is already done in 2015. And there is still, nowadays your eyes recognitions, in future your blood samples, everything has been taken, and more information will be taken by this community, right? So thought recognition. So what you are thinking, now people are going into that direction to mapping your brain. What is happening? What kind of thoughts? What kind of thinking, imagination in your mind that can be scanned by using the squid. Nowadays, squid devices where encephalography, encephalography will be used, and you will have the helmet. We can just wear those helmet, and other person will understand about, like, instead of having the lie detection test, directly you can put that encephalographical helmets and you will map your thinking, right? So how brain thoughts? So that kind of thinking imagination or thinking mapping will happen because of this kind of smart devices using the nano speeds and nano encephalographical devices, right? Emotional control chip for the criminal. Can we put the chips inside the body so that it will control your thoughts and emotions of these particular criminals? So if someone wants to kill somebody, we can give him command or it can control his thoughts, and that kind of incident will be avoided. Okay, so these are the futures, like moon-based villages. So can we go on the moon and make such kind of villages by 2040? So these are the forecasts for the futures, and you people can also think a lot of things about the future, like like Feynman. Feynman has thought about miniaturization idea in Caltech. Similarly, we people can also thought about some beautiful ideas for the future, and we can make it happen through the nanotechnology and now emerging field of artificial intelligence. Okay, I hope you people are getting what I mean to say, right? So, on million developments, what are the important goals now? Immediate goals has to be set up by the scientific community and material scientists and nanotechnologists. First one is we are scarcity of water, and at the villages there is a safe drinking water required. So water is a very important area where these nanotechnologists and nanoscientists should play a role. Improving the food security is another area. Another one is health diagnostic. As this corona virus and COVID pandemic, we understood how important the health concerns are, and therefore the diagnostics, monitoring, and screening of the health is very important. So can we make such kind of brilliant devices, brilliant diagnostic kits, and brilliant protection kits as well? Then environmental pollution has reduced a lot, but still once this lockdown will open, and then if everything come back into the road, again we will find out there is environmental pollution happen. And how we can tackle those situations, like we can capture the CO2 and convert it into the methane or any useful things. So that is the good environmental impact which can be taken up by nanotechnology. Then another thing is energy storage area. That energy production conversion is a huge area because huge demand of the energy at the moment, and the global partnership by using this kind of nanotechnology. Okay, so what is the anti-nanotechnology? Because since beginning, since almost 1.5 hours, we are listening about the nanotechnological advance, nanotechnological application, beauty of nanotechnology, what is the fancy, what is the art, all those things. But what is the anti-nanotechnology? Because nanotechnology is too much hyped, right? Huge expectation from the nanotechnology. Like see in the COVID, just last 2 or 3 months, there is a huge expectation from nanotechnology that nanotechnology should deliver diagnostic kit, nanotechnology should deliver PPE kits, or nanotechnology should deliver the medicine, vaccine, and so many things. So there is a huge burden on nanotechnology and huge expectation and huge hype. So that has to be avoided. We should become a realistic at the moment. So unfounded phobia about the environment and health. As I said just before, that toxicity, the nanoparticles can go into the body, agglomerate, and form the cancer. Such kind of rumors are there, right? And so these are unfolded phobias about this environmental degradation or health degradation due to the high surface energy of these nanomaterials, right? Therefore, what we need to do is we need to have the balanced approach to convey our excitement about the nano and possibility of our long-term solution. So we have to keep ourselves motivated at one side, keep our excitement up, but at the same time, we should find out the possible long-term solutions, right? Just to make a fancy or just to have an art, doing this nano doesn't make sense. Curiosity is one side and utility and application should be the another side, so that we will have the long-term solutions using this nanotechnology. So what are the career perspectives in nanotechnology at the moment? It will change definitely before corona, after corona. Now world is about to divide before DC and after DC. Similarly, now before pandemic and after pandemic, like before COVID and after COVID. So what happened is, okay, so what happened is before COVID and after COVID. So similarly, this career perspective probably after COVID will change drastically, right? But at the moment, what is happening is in the career perspective, the scientists are getting less paid. They are having less payment. But what is the advantage or what is the excitement is that there is huge excitement in nano. Okay, so there is a novelty. So you will enjoy working in nano, irrespective of the pay. So what is there is negative point is you need to work for the longer. In the laboratory, scientists are doing experiments. It takes longer time. They have to do n number of experiments and get the results. They took longer times, longer hours. They need more patience to get your work done. But at the same time, you have a freedom in working. You can implement your ideas. You can implement a lot of things while doing your own experiments. So you have a lot of freedom doing those experimental works, right? So one time you need patience. Another side you have the freedom, all freedoms. So that is an advantage. So here many months you will have with no results. So there you little bit, your energy go down. But once you get the results, your rewards and glories of the success go at the international level. So you will get recognized at the international level. So that is an advantage of having this kind of nanotechnological work. So this nanotechnology work requires long training because this is not as simple. You need huge training on nanotechnological tools like characterization tools, your applications tools, your synthesis tools. So long training is required, but it has huge social benefits, right? So once you get trained, you are a skilled person and it gives good benefit to the society. But in career perspective, this is very highly demanding. But what you need to have is really questioning attitude, right? Then you need to have the special skill sets at one side, but imagination is more important than your knowledge, right? So as Einstein had said, so you have good imagination, you can become a good man. So let's have a look on this quote of this gentleman. Quote of this gentleman, Claude Strauss. What he said, a scientist is not a person who always gives the right answers to the questions, but he is one who asks the right questions. So I hope all of you will have very good questions, and it shows that you people will be very good scientists, right? Rather, I may not give you the right answers, but your good questions will always make you the good scientist. Okay, so this, I would like to just suggest you one book that is Michael Kaku, who has wrote The Physics of the Future. So how the virtual world will happen, how the biological world will happen, what is the pandemic situation at the moment we are facing. It has been written by this gentleman. Michael Kaku is a theoretical physicist. He has taken the interview of 500 scientists across the world, and he had decided how world will be at 2025, how world will change in future, and how the world will transform our lives. So in his book, he has written not only the nano, chemistry, physics, or engineering prospect, but he overall covered all the science, nuclear science, and all those things, IT and in artificial intelligence, all things he has covered in this book. So I will refer this book. Those who are interested can go and read this book. Okay, so I hope, and up to this, you have enjoyed this conversation and this talk to nanotechnological tool. But now it's time to come up to our own home. Let's say this is our second home, that National Center for Nanoscience and Nanotechnology. Here, I would like to show you something about our center. So our center is housed the modern building in Kalina campus, right, which is having area about 120,000 square feet. You see the picture, night picture we have taken here. This is the Nanotechnology Center in Kalina campus, and I welcome all of you to visit sometime to the Nano Center and understand about it. But I will little bit showcase about the activity of this Nano Center. This Nano Center is a state-of-art facility in University of Mumbai, right? And we have clean rooms. Okay, this clean room area is almost 8,500 square feet clean rooms. You see here in the picture how these clean rooms look like. So what it mean by the clean rooms? Clean rooms are, they are allowing very tiny particles and very less number of, here you see the class 10,000, class lakh, class 1,000 and class 100. It means 1 cubic centimeter square, you will have only 100 particles, okay, less than 1 micron size. So this is a sort of clean rooms standards we have, and we have huge clean room, 8,500 square feet. This is the largest clean room in the world. Okay, so no any institute, even IITs or ICER or any institute have this big clean room. So 8,500 is really huge area. Our whole ground floor is about the clean rooms. And usually the nanomaterials, or if you are doing nanotechnology research, you must have these kind of clean rooms. Because even a single dust particle, when you are making the device, even a single dust particle can reduce the performance, or which can, it means which can disturb or which can distract your device, and then it will not show the proper features, right? Therefore, you need a really very high clean environment, and therefore we are having this kind of clean rooms, where clean room 10,000 we use for the synthesis and materials fabrication. Class 1 10,000 we use for different characterizations tools like spectroscopy, microscopy, and imaging, all those things. And this class 100 clean room will be dedicated for the device fabrications. So this is the really beauty and state-of-art facility we do have. I will show you some of the images of state-of-art facilities available in the center. You see here the clean room with class 100, 10,000. This is class 10,000 clean room. Here you see the right image of Versa 3D. That is, you see this Rajabhai Tower, carving of Rajabhai Tower on this tungsten tip was done by this instrument. Here we use focus ion beam as well as electron beam to lift off or to write on a nanoscale. So you can write your name on your hair by using this machine. Okay. So this is high-end equipment we have in our laboratory. Let's have a look on another instrument, which is Conta ACM. That is a scanning electron microscope where you can see your nanomaterial, synthesized nanomaterials, and the resolution of this machine is around 10 nanometers. So up to 10 nanometers, you can go by using this machine. Here you see down, there is a specific platform. So this platform is anti-vibration platform. Because of this platform, the resolution of this system is very high, right? So such kind of anti-vibration platforms are generated throughout our clean room for various characterization systems. This is another big system. This is MBE system, where we can grow, we can grow the atom by atom, single atomic layer on silicon vapor by using this MBE. So this MBE is dedicated for the silicon, right? And this is atomic layer deposition of any material can happen using this MBE, and which can be used for the electronic industries, right? Dr. Harshvardhan Bhatkar from Nanoscience Center is looking after this facility, and which is one of the state-of-art facility in Nanoscience Center, which is having only this bigger MBE at, I think, in IIT only. But this is the custom-made and German-based biggest instrument in our Nano Center. This is another beautiful tool, which is PLD and PED, pulse laser deposition system, and pulse electron deposition. So here we can deposit thin films by using pulse laser deposition. Any inorganic material can be deposited on any substrate by using the PLD. And if we want to deposit any polymeric material, we can use this PED, right? Pulse electron deposition system. You can deposit Nafion or polymer, any polymer you can deposit by using this kind of electron beam. So this is another important tool we do have and this is very high-end equipment procured from the USA Neosera. And this is the only facility, I think in Mumbai at least we have, this is the good facility with PLD, PED. This is another important XPS system, C60 Dept profiler, where we can do the XPS analysis. Same time, if you have the multi-layer stacking, you can have, you can lift off each individual layer and do the XPS at the interfaces. So interface study also can do by using this XPS. And this is very rare system in India. Very 2-3 institutes in India having this kind of system. Recently, IISc Bangalore has bought this system, and IIT Kanpur was having. And this is the first system in Mumbai University. And it is very sophisticated equipment. We got so many samples across the country, even from international, different samples are coming to our center for the characterizations as well. You see here, there is another PPMS measurements, so physical property measurement system, which we can go up to very small level, that is 2 millikelvin temperature we can go. And from low temperature to high temperature, we do all electrical measurements, electrical and magnetic measurements by using this PPMS system. 3D profilometer. This 3D profilometer, you can have the three-dimensional image of your devices, and you can visualize all those patterns of your electronic devices by using this. We have the nano IR spectroscopy. We have the nano indentation for different mechanical testing of your films and your nanomaterials. Later, so all these facilities are there in the nano centers, and this nano center we have focused on different things where we have decided to have the global collaborative R&D research projects. So we have decided to involve in nanotechnology education initiatives, another innovation parks for the industries, South-South collaborations in nanotech. South-South, it means from Mumbai onwards to, let's say Chennai onwards or other stuff. Then green nanotechnology, so green solutions. So these are the different thrust areas where our faculties are involved in the research. Energy and environmental is one of the thrust area of our research. We have the bio nano foods and agricultures, nanomedicine, healthcares, security, safety, functional nanomaterials, and nano devices. These are the different thrust areas our faculties are involved in the different research projects, and they are working on these different things. So here was, just recent media attraction of our research, what we have done in our laboratory regarding the battery materials or energy storage materials. I would like to show you one video which my students has done this video. You see here, these are the cells. Okay, so these are the supercapacitors actually. 2 supercapacitors are arranged in a series. Okay, and they have charged just for at 3 volt. We have charged these 2 supercapacitor devices. Let's say for 21 seconds, right? After charging 21 seconds, these 2 devices, we have just given a load of this fan to that, and you see how these devices has been working. So these devices are made up of these nanomaterials, which I shown earlier in the slide, that we have developed different number of nanomaterials, and this has been made by the WO3 nanoflex, right? And you see here how these devices are working. So this is nanomaterials, and weight of this nanomaterial is very less. Only 10 milligram of this weight of nanomaterial is used to make a single device. So almost 20 milligram of the weight is being used to prepare this kind of nanomaterials, right? And this is the similar thing. We have arranged the 2 different devices, and here is the LED, and the output of LED is 1.6 volt, right? So if you charge it for the 15 seconds, it will survive for the few minutes, right? So it will survive few minutes. I will show you in a minute. So this sort of energy materials work is happening in our laboratory. And my student Shobnath Gupta and Harish Nishad, they both are working on this kind of energy devices by using different nanomaterials. So here you see the almost 31 seconds that devices were charged, and how long it will blow this kind of LEDs. So it will blow the LEDs for few minutes, let's say 4 to 5 minutes or more than 5 minutes. So that's how we are doing this kind of research at the laboratories. Okay, so let me go ahead and what would be the future. You see here, this automobile industry is huge, and this picture has been taken from Volvo website. So this Volvo is trying to convert this complete body of this car by using the batteries. So you have to just put the different battery layers on the car, and then that battery will store the energy, and that energy will be utilized to run your car. So this would be the future of technology and materials in the energy sector. With this, I would like to show you what sort of courses are offered in our nanotechnology center. Here we are offering 2 courses. One is MSc Nanoscience and Nanotechnology. MSc course is for 2 years and 4 semesters. Out of that 4 semesters, the last semester is completely dedicated for the research project, so that students will learn how to get trained on the research and research instruments like characterization devices, characterization techniques, and how to do the research. So they get a basic training of research before going out with their master's degree. And PhD in nanoscience and nanotechnology, the advantage of doing PhD at this center is we have the state-of-art infrastructure facilities available. So it will speed up the PhD work, number one. Number two, we have good expert guidance. We have good industrial collaborations. So the student will get a very good experience working in the laboratories, hands-on training, industrial collaborations, and expert guidance, so that the PhD quality work can be done at the center. Also, our faculties are publishing very good research papers. They are filing different patents, and we have the various research projects in our laboratory. We have the funds from DST, SCRB. We have the funds from DRDO. We have the funds from the industries as well. And not only this, but our faculties have huge international exposure. So we have too many international collaborators. Recently, we have the collaborators from Australia, Deakin University. We have the collaborators from the USA. We have the collaborators from the Europe, Korea, and so many places. So here, I would like to give you some statistics about the admission, how the admissions happens at the Nanoscience Center. So you see here in MSc during 2017 and 18, because we are admitting students through the entrance exam. Our center is conducting the entrance exam for the MSc students. So first year, what happened is we were having almost 80 applications, right? 80 applications. 80 people appeared for these entrance examinations. Out of that 80, only 20 get selected, admitted, right? So you see the rate of the admission at the Nanoscience Center. So out of 80, only 20 get admitted, and out of that, have large number of girls. So this is the very good thing at the center. And here the boys' strength is around 8 to 9 and 12 girls. Similarly, MSc next year, 18 and 19, again, we will have more than 80, almost, 85 to 60 students. And out of that, again, 20 get admitted, right? And in that, we have the large strength of boys. Similar thing in the PhD, you see here, more than 50 applications were there in the first year PhD called 15-16, and we have admitted only 10 number of the students, right? 5 girls and 5 boys. Then in 16 and 17, our second call had come, and we were having almost more than 25 applications, and only 10 students get admitted for the PhD course. And now new PhD advertise and MSc advertise, admission notification will come out this year again. So here I would like to see what people are thinking, or what I'm telling about the Nanoscience Center is the different scenario. But what people thinking at the international level about this Nanoscience Center, that I want to show you. In 2015, these different Nobel laureates, they visited to the Nanoscience Center, right? They visit the Nanoscience Center, and what they made the statement about the Nanoscience Center, I will just read for you. This is Professor Paul Nurse. Paul Nurse is Royal Chemical Society, RSC Chemical Society chairman, and he is the Nobel Prize winner of the medicine. What he said is, visit and impressive battery of equipments and people. Good luck with your future research. You see here. So this is the comment by the Paul Nurse made about the Nanoscience Center. This is Professor Randy Shekman, who has also won the Nobel Prize. He is from University of California, Berkeley. And he visited to the Nanoscience Center, and he said, exciting beginning. Now the challenge is to fill the building with excited young scholars, right? So he was impressed by the infrastructure, what has created in Nanoscience Center, and he is expecting that more young scholars like you people can come and join us for this journey of nanotechnology. This is another Nobel laureate, Robin Warren from Perth, Australia. And he was so nice to be there 3-4 days at Nanoscience Center and observe these activities at the Nanoscience Center. And what he said about the technology or this department is a fantastic laboratory with a wonderful equipment, and hope you can advance the project as you suggest, making money rather than just opening it. So what he said is, you have the wonderful equipment, and rather than just having this kind of equipment, you just make huge money out of this kind of research, right? And another one is Muhammad Yunus. He is also Peace Nobel Prize winner from the Bangladesh, right? You people know him, I think. So this Muhammad Yunus, what he says, what a great opportunity to see the great lab in University of Mumbai dedicated to nanotechnology. A lot of things can happen to improve the lives of poor people. It direct our research in that direction. So what he said is that you have the very nice infrastructure facilities for the nanotechnology. So you do such a good things in your lab so that it will benefit the poor people as well. So this is the impression of these Nobel laureates about the Nanoscience Center. So I wish you people will join the journey of the nanotechnology. And here are some, visiting snaps. And this guy is the Abel Prize winner. Abel Prize winner of, this is the mathematics most prestigious award. Most prestigious award is getting. This is, you see this Adayanath. Adayanath is a Nobel Prize winner in the chemistry, right? She is a chemistry Nobel Prize winner, Adayanath. And she was visited to the Mumbai University during Indian Science Congress, right? Okay. And this is the theme of our Nano Express 2019. The last year we had a very good national conference. And this is huge crowd of organizers of Nano Express conference, and which has a huge success. We have the speakers from IIT Delhi directors. We have the speaker from IIT, different IITs, and it was a grand success of the Nano Express conference. And I hope that next year, probably you people will also join us for this next Nano Express conference. And at the last, I would like to acknowledge former director CSIR Sikri and CSIR NCL, and presently the Dean of ISER Tirupati, Professor Vijay Mohan Pillai, because I started my nanotechnology journey through his lab in NCL. Then former Chief Scientist CSIR NCL, Dr. I.S. Kulla, he was also there. I was working under his guidance in NCL Pune. Then I would like to acknowledge the Director, National Center Nanoscience and Nanotechnology, University of Mumbai. I acknowledge my NPDF fellow, Dr. Jyoti Sharma, my PhD scholars, Shobnath Gupta, Nanda Desai, and Harish Nisha, my group PhD students. Then I would like to acknowledge our national international collaborators, Dr. Carmine Granata, my PhD advisor, Dr. Chiro Napi, Dr. Wilfried, Dr. Ulrich Luders, Dr. R. Ramesh, and my colleagues at Nanoscience Center. So with this final quote of Richard Smelly, the nanotechnology holds, final quote, nanotechnology holds the answer to extend their answers to most of our pressing materials need in energy, health, communications, transport, and foods. Professor Richard Smelly, thanks a lot. I would like to answer the questions.
Yes, sir, please. Thank you, sir, for your inspiring lecture. During your lecture, you have thrown light on nanomaterials from past to future. Definitely, after listening your lecture, it must have inspired all of the students, research scholars, and faculty members. And definitely, there will be a number of questions in the minds of students. So we will have the question answer session right now. We will take just few of the questions and later we will try to answer by the mails only. So there is a one question from the student. Color changing material can be made up of which method? Bottom-up approach or top-down approach?
Any approach is fine. Use any approach, either top-down or bottom-up approach. Just scale matters a lot. If you go yeah.
Praveen sir, there is one question from the student. How fire resistance material can be made by using nanomaterials?
Yeah, it is actually the shielding. Fire resistive material is nothing but electromagnetic shielding. So usually the carbon materials, carbon nanomaterials will be very helpful to use this kind of shielding materials, right? So it depends how it can be interact with your lighting. So you should have this kind of carbon-based material which will absorb these shock waves, and there will be the fire resistive material can prepare with this.
So there is also one more question. How in 18th century the nanoparticles were used for the construction or preparation method? Which methods they are adopting? Just now in
Yeah,
your lectures you have mentioned the Rajabai Tower.
yes, yes, yes. Actually, that time, the Roman glasses or those architect, they were not knowing that these are the nanomaterials, but they were
Yes.
just, heating and burning those kind of metals, and they are forming these kind of alloys. And they were not knowing whether it's nano or not, but they were finding out by using the systematic method, it is showing the beautiful colors, right? So they are just changing the concentrations, and they are using the different heat treatments to these metals and try to get this, embed this into the glass matrix. And they were seeing this, okay, this is, they have done it's all trial and error method. They were not knowing that time it is a real nano alloys or not. And during that time they were having the different defects, like just gold. They were not knowing that the gold nanoparticles are also in, or they were not knowing that whatever the tools they are using, they are leaving the atoms, atomic impurities into that alloys, right? So it was unknown discovery, and later on, once nanotechnologists tried to explore those things, they understood that there is a nano alloys.
Acha. Thank you very much, sir. There are very n number of questions, but it is very difficult to take all the questions as we are quite extended session. From last 2 hours, you are just continuously talking. So now we will take the live feedback from one of the participant who are joined from Iran. I request Dr. Mehboobe Manchouri, which is joining from Islamic Azad University from Department of Chemistry. Can you please give your feedback, madam?
Hello, can you hear me?
Yes, yes, yes.
Yeah. Hi, thanks to Dr. Parveen and the organizer of webinar. In overall, I'm very satisfied with this good presentation. Thank you, Dr. Parveen. It was very informative, and the idea and concept were extremely clear. But there was some technical issues that prevented from joining me from meeting at first, but in midtime it was good. The subject of seminar was very interesting, and the presentation was in right order and right level, but I didn't find any as Dr. Parveen talked about graphite and fullerene and CNT, it would be more interesting if you include your presentation about graphene and graphene also and their properties in medical, actually in drug delivery and some other medical application, I think.
Okay, thank you, madam.
Since I have been in Punjab University in 2007 for my postdoc, it was very memorable for me being among very many good Indian people. It was very enjoyable. Thank you.
Thank you very much, madam. Now I request any one of the student participant who can live feedback. Please unmute yourself and you can talk. Voluntarily you can talk. Okay, I think there will not. Now we will move toward the last session, that is vote of thanks. I request my colleague Dr. Kirti Kulkarni madam to please propose vote of thanks for this session. Madam, please.
Yeah, thank you, sir. Am I audible?
Yes, yes.
Yeah.
Yes.
Yeah. Good afternoon, all of you. It is said that science is a brain of thinking much more than the body of knowledge. Really, science is life. Today, Dr. Praveen Walke sir has thrown ample light on nanomaterials, its past, today's scenario, and future application. It is very useful and helpful for our students as well as the faculty in their further and future research. Really, the word nano means small, but its applications are really, really big. Sir also explained about interesting topics like robots, artificial intelligence, mind mapping, emotion control instrument, etc. Sir, really, heartiest thanks to you for this wonderful, wonderful session. Thank you, sir. I express my deep sense of gratitude toward our principal, sir, Dr. M.R. Mishram, who is continuously support us for every activity. Sir, without your support, it is not possible for us. Thank you so much for this opportunity. I would also like to thank our Vice Principal, Dr. Anil Patel, sir, for his enthusiastic participation in this webinar. Though sir is not from chemistry background, his presence really graced our webinar. I would also like to thank our head of department, Professor Sonawane sir, then Payekar sir, Pawar sir, and all my colleagues from chemistry department of GS Jawhar for their efforts taken for this webinar. These non-stop efforts only have made this event very successful. I'm also thankful to Dr. Mahesh Mudgal and Mr. Nikhil Murankar and all the technical team for their throughout all my dear participants, students and faculties. Without your support, this webinar could not be a successful event. So thank you so much for your participation and your support. Thank you one and all of you. Stay home, stay safe, happy learning. Thank you.
Thank you, madam. Now there is a one information for all the participants. We have posted a feedback link in the chat box. It is mandatory to all the participants to fill up the feedback form. Once you fill up the feedback form, you will get the certificate for attending this particular webinar. That certificate will be mailed to your registered mail ID. So all the participants who are joining from the Zoom meeting app, the already we have posted a feedback link in the chat box. Please fill the feedback form. Those who are joining from the YouTube, also we have posted feedback link at that point only. So all are requested to please give your feedbacks. You will get certificate for attendance. Thank you very much.
Thank you.
Shall
Have a
we
nice
end up
day.
the meeting?
Wonderful lecture. Yes, feedback link is
Shall
posted.
I end up the meeting?
Yeah.
Yes sir, yes sir.
Yeah,
Thank you,
thanks a
Praveen
lot.
sir.
See you.
Thank you, sir. Thank you.
Morankar sir, you can end up the meeting.
सर भरू
Okay,
दे 2 मिनिटं एक
okay,
5 मिनिटं फक्त.
okay, fine, fine.
those who have filled the feedbacks, they can leave the meeting. You will get your certificate on your register mail ID. Thank you very much.